In the early days of electric vehicles, the industry relied on highly reactive battery chemistries that carried a persistent risk of catastrophic fires. That risk was engineered out of existence with the introduction of LFP, or lithium iron phosphate batteries, a highly stable chemistry that refuses to ignite. But that stability came with a steep cost. Early adopters had to accept three major compromises: sluggish charging speeds, heavy physical weight, and range drops in freezing temperatures. To compensate for the lower energy density, engineers maximized the physical space inside the pack. They created the long blade battery format, a stretched rectangular cell that quickly became the undisputed industry benchmark for LFP vehicles. Now there is a challenger. Automaker Geely recently released their short blade battery, also known as the Aegis, with the specific claim that it eradicates those remaining LFP compromises entirely. For anyone evaluating a modern EV investment today, determining whether the short blade is a legitimate technological leap or just marketing jargon is the single most critical factor to consider. The most obvious difference is the physical geometry. The short blade measures roughly 580 millimeters in length, effectively cutting the traditional long blade down by 40%. You cannot simply drop this smaller cell into an existing car. This physical shrinkage forces automakers to abandon older vehicle designs and build entirely new, highly specific platforms, like Geely's GEA architecture, just to house it. In these new architectures, the battery pack serves as the physical, load-bearing chassis of the car itself, integrating directly into the structural frame. This structural overhaul raises a practical question. Does shrinking the battery cell actually yield measurable performance data that changes your daily driving experience? To answer that, we have to strip away the branding. We need to directly compare the hard data between the established long blade and the new short blade across charging speed, climate resilience, and total lifespan. The primary physical bottleneck that prevents long battery cells from absorbing electricity quickly is internal resistance. Internal resistance is the natural opposition a battery presents to the flow of current, which generates excess heat and slows down the charging process. When you shrink the blade length to 580 millimeters, you physically shorten the distance the electricity has to travel. That inherently lowers the internal resistance. Geely also integrated microscopic carbon nanotubes into the cell design. These act as straight, unobstructed highways for ion transmission, allowing particles to flow rapidly without bottlenecking. This matrix compares the charging data directly. For the long blade benchmark, the maximum average charge rate is 1.61 C. A C rate is a metric that measures the speed at which a battery charges relative to its maximum capacity. At 1.61 C, it takes roughly 26 minutes to charge a long blade from 10 to 80%. For the short blade, the average charge rate jumps to 2.45 C. It completes the exact same 10 to 80% charge in just 17 minutes and 4 seconds, a 33% reduction in charging time. The architectural trade-off here is absolute. This charging speed cannot be retrofitted into older EVs. Accessing it requires buying into a next-generation platform designed specifically for this lower resistance. Achieving a 17-minute charge time aligns the EV charging process closely with the cadence of a traditional gas station stop. This effectively neutralizes the primary argument against taking LFP vehicles on highway road trips. Then there is the historical winter range tax. LFP batteries are notorious for suffering severe capacity drops in freezing temperatures, which has deterred buyers in cold climates for years. The short blade combats this chemical lethargy using a combination of its lower internal resistance and new film permeability additives that help ions move even when the temperature drops. Looking at this vertical bar chart, comparing cold weather capacity retention at -30 degrees Celsius, we can see the benchmark failure point. A standard long blade battery retains only 78.9% of its operational capacity. Under the exact same -30-degree environment, the short blade retains 90.54% of its capacity. This 11% delta in capacity retention expands the geographic viability of LFP vehicles. Drivers in harsh northern climates can now rely on LFP technology that previously would have stranded them in sub-zero temperatures. Moving from chemical resilience to physical durability, this architecture relies on CTB, or cell-to-body integration. Cell-to-body integration means the battery is not a separate component, but the actual structural floor of the vehicle itself. During validation, the short-blade architecture survived extreme kinetic trauma. It passed an 8-needle simultaneous puncture test and withstood a 36-ton tank crushing it. If the pack is punctured, self-fusing aluminum foil technology on the electrodes instantly creates an insulating layer. This entirely blocks the internal short circuits that lead to thermal runaway and fires. Beyond physical armor, the smaller size and multi-element doping significantly slow down the internal chemical degradation rate of the battery over time. The official cycle life data rates the short blade for 3,500 charging cycles. Translated into real-world distance, 3,500 cycles equates to 1 million kilometers of driving, with minimal impact to the overall range. Framed in years, for a driver covering 20,000 kilometers annually, the battery is engineered to remain in operational service for up to 50 years. But the CTB integration introduces a severe trade-off. If the vehicle suffers catastrophic underbody damage, modular repair is nearly impossible. You are mandated to pay for a full, expensive pack replacement. Sacrificing modular repairability is the price for a pack that eliminates fire risk and offers a 50-year degradation timeline. This engineering shift prioritizes long-term vehicle ownership over the repairable but more volatile designs of the past. Zooming out, Geely's GEA architecture operates as a holistic system. The Aegis short blade works in tandem with a highly efficient 11-in-1 e-drive motor and an advanced thermal management system. To evaluate this system, we can map EV purchases on a matrix. This quadrant chart balances a battery's chemical volatility and max range on the y-axis against its total longevity and safety on the x-axis. Standard NMC battery chemistries, which stand for nickel, manganese, cobalt, score high on the volatility and max range axis, but lower on the longevity axis due to faster degradation and inherent thermal risks. The short blade architecture maximizes the longevity and safety axis while accepting a definitive cap on its absolute maximum range. The short blade does not try to be the ultimate 500-mile road trip vehicle. It is a deliberate engineering choice that prioritizes total generational lifespan over chasing maximum range figures. This split-screen scorecard graphic evaluates whether a short blade-equipped vehicle, like the Proton E-Mass 7 or Geely EX5, fits your specific driving profile. The perfect fit is the pragmatic long-term buyer. If you intend to keep your car for 7 to 10 years and demand that your residual value is protected from severe battery degradation, this architecture serves you. We can add the climate challenge driver to that perfect fit profile. The 90.5% winter retention data validates that the historical LFP cold weather penalty has been eliminated. However, you should look elsewhere if your singular priority is driving 400+ miles on a single charge without stopping. Those drivers will still need to accept the risks associated with NMC chemistries. Right-to-repair advocates should also avoid this platform. The highly integrated cell-to-body design directly opposes any modular, at-home battery swapping. The short blade indicates that LFP technology has reached a point of maturation. By matching the charging speeds and climate resilience of internal combustion alternatives, it removes the remaining technical barriers to mainstream electric vehicle adoption.